So we'll carry out our discussion from the last couple of lecture about the time domain analysis. So far, just to recall very quickly, we have done, we have seen the transient performance specification and also the steady state error. So for both these performance specifications, we have seen that how do we compute the maximum overshoot, settling time, peak time, and also the rise time. And for the steady state error, we have seen how to determine the steady state error for different types of inputs. Say for example, unit step input or the ramp input or the parabolic input. And what is the relationship between the steady state error and also the type of the system. So today we will carry forward this discussion to see that if our system is not first order or of second order, or if it is of higher order, let's say more than two second order system, then how we can analyze those specifications, because the formulas we had seen specifically for the first and second order system won't be applicable to the higher order systems directly. Okay, so we shall see that if you are given a system with a higher order than the first or second, then how you can analyze the performance or the performance of the system. First, second, we shall also see that if you add some additional poles and zero to a given system, that how this will impact the closed loop system. Okay, so the later analysis would help us to, or whatever the concepts we would introduce in the later point would help us to analyze the designing of the controller basically. Okay, so before starting with this, let's see that if you recall that we, for the second order system, we have two poles where we have minus xi omega n plus minus j omega n under root 1 minus the square. Okay, and this term we have defined as omega d, and this one we have defined as alpha. Okay, now in the pole 0 map or in the s plane, we have g omega x is sigma, and this is our s plane. Okay, so let's say we have any pole, a complex conjugate pole located at this point. So what does this geometrically means? The roots what we have seen. So if I draw a straight line from either of this pole, because the length of the length of this line would remain the same, either I draw it from here or I draw it from here. Okay, so this line, the length of this line would be omega n, and the projection it would have on the y-axis, it is here we would have j omega d, and here we have minus j omega d. Now this point would be on minus xi omega n. Okay, and the angle it what it makes a theta, because this uh, poles are given in the rectangular coordinates. So if you, because this is a complex pole, so if you want to represent in a polar coordinates, then with the help of this theta you can write the location of the poles in polar coordinates. Okay, so this is the pole plot for an underdamped second order response. Now we shall first of all see that whatever the transient specifications we had seen so far, what is the geometrical significance of those specifications on the pole plot for an underdamped second order system. Okay, just to write very recall the formulas for. So the formula for TP we have is pi upon omega d, and for TS we had seen is pi upon this alpha. So if the alpha is it's better to write it's minus alpha. Okay, so the we would have alpha here. Okay, so these were the formulas we had seen for the settling time and the peak time. Now on the S plane once again, let's mark 2 points. One one point is this one and another point is this one, meaning to say in the first case, okay, I shall use different. So these are the two cases we have. Okay, so this represent case 2, and in this color we have case 1, let's say. And these two cases are basically that we have two different location of complex conjugate poles. So if I draw the line here, let's okay. So first of all we shall see the case 2. Now for these 2 points, you see that the settling time depends on the alpha, and this line basically, which is the damping line. So if I draw this, excuse me, so let's say we have these two damping lines for two different cases, and this line basically gives us the percentage overshoot, and similarly this line will give us the percentage overshoot. Okay, so with the location of this pole we have this TP1 here, and this line, the vertical line, we have TS1. Okay, so this is our case 2, I will call it TP2 and TS2. Similarly for this line we have this line is TP first and this one is TS2. Okay, so the idea here is to show that the peak time for the first system, for the first scenario, and this is the peak time for the second scenario. So you see, if the pole is at this location, meaning to say more closer to the origin on the real axis and farther on the imaginary axis, so we would have the peak time greater than the peak time of the other case. Similarly, but the settling time would be lower for this case as compared to this one. Okay, so this is how you can plot the different transient performance specifications on the pole zero port. Now the question arises, if we have the additional poles. Okay, so to introduce the concept of the additional pole, let's see. Okay, consider the scenario. So we have seen the first order system, we have seen the second order system. Now if we want to see the third or higher order system, as I said that the formulas what we have derived won't be applicable directly, but they can be approximated quite close enough. So particularly for dealing with third or higher order system, we introduce the concept of the dominant poles, meaning to say that if you are given with a third order system, then it can be approximated as a second order system that has just two complex dominant poles. The third pole won't be much dominant in contributing the or impacting the behavior of the system. So to analyze this scenario, we will see that we will consider the case where we have two complex conjugate poles. Let's say the two complex conjugate poles are located at minus xi omega n plus minus j omega under root 1 minus xi square. And the other pole is a real pole located at minus alpha r. So in the second order system, we had only these two poles. Now we are adding an additional pole, and which is a real pole. So if I write the output transform of this system, I would have, let's say, C of s is equal to some a by s. This s comes from the step response plus bs plus xi omega n plus c omega d divided by s plus xi omega n square plus omega d square plus d upon s plus alpha r. So I have written directly by using the partial fraction of the overall expression, where c is the output transform and 1 by s is the unit step input. And in the time domain, this c of t is given by a u of t. U is some step signal plus e to the power minus I omega n t b cos omega dt plus c sin omega dt plus the next contribution is because of this term, and this is the pure exponential, so d times e to the power minus alpha rt. Okay, so on the pole 0 plot in this figure A, you see three different cases: case 1, case 2 and case 3, where the location of the complex conjugate poles are fixed. We haven't changed those poles of the second order system, but what we are interested in, that if I add up an additional pole on the real axis, then how the location of this pole would impact the behavior of the system. So in the first case, alpha r1 is here, that is to say closer to the dominant poles. So here the dominant pole is our complex conjugate poles of the second order system. In the case 2, it is farther, and in case 3, the pole is located at infinity, minus infinity. Okay, so that's why it is not marked on the pole 0 plot. Okay, so for a specific system, here we have drawn the different responses, that if in the third scenario, this is the response c of t, that in the third scenario you see that the response almost matches with the second order system. In the second case, where we have alpha farther to the dominant poles, then this is the response of the system. And if alpha is more closer to the dominant poles, then we not be approximated by a second order system. The reason is, let's say if alpha of r uh, is much greater than yours xi omega n, which is our second case or the third case, so this pure exponential term will die out much more rapidly than the second order underdamped step response. Okay? And if the pure exponential term decays to an insignificant value at the time of the first overshoot, then the parameters such as the percent overshoot, settling time, and the peak time will be generated by the second order underdamped step response component. Okay, and the total response will, for the third case, will approach that of a pure second order system response. Okay, this we can see by an example also. Just to better understand the scenario, let's say we consider three transfer function t1 of s as some 24.542. So I'm considering the example 4.8 from the one of the textbook by Norman Nice. So we have this t1 as s square plus 4s plus 24.542. Okay, I have t2s, the second transfer function, which is I have t1 multiplied by 10 upon s plus 10. Okay, so I have added one additional pole at minus 10 in the transfer function t2. Now I have t3 of s, which is t1 of s times 3 upon s plus 3. Okay, so this is a pure second order system. Here the pole, I would say an additional pole at minus 10. Here we have additional pole at minus 3. So we will see three different responses with respect to we'll see two different responses with respect to the second order system. So C1t, if I compute the response, would be given by 1 minus 1.09 power minus 2 cosine 4.532, and C2t, we have an additional term because of the exponential term, and in C3t again we will have some additional term because of the pole located at minus 3. Okay, in all these three responses you will see that the frequency component of the sine cosine of the sine cosine term has not changed because of the addition of this pole. Okay, and for these three responses this is the graph you would obtain. So here again, if we see or if we apply the previous analysis onto this, we know that the poles uh, that this pole minus 10 is located farther from the dominant poles of the second order system, and this additional pole minus 3 is located near to the dominant poles. So it is expected that whatever the response we would obtain for C2 would be much closer than of C1, and the response of the system C3 cannot be closely approximated with the response of the C1, and this is what has been shown in the graph, that C1 is the response of a pure second order system and CT is the response of a third order system in which there is an additional pole located at minus 10. So you see the peak time and the maximum overshoot is almost equal. Okay, but for C3 it is much different from that of the C1. Okay, so let's see a deeper analysis. So now we shall see that if I add a pole into the forward path transfer function, considering a unity feedback system. So here we will consider two cases. First, we will add a pole into the forward path, and we add a pole to the closed loop transfer function. Okay, these two different scenarios we will see, and we shall also uh, extract that how it impacts the transient performance of the system. Okay. So consider this transfer function where this one is the forward path transfer function we had earlier. Now in the forward path transfer function, an additional pole has been added, and this additional pole is located at s is equal to minus 1 upon tp. Okay. Now if I form a closed loop transfer function of this forward path transfer function, I would have g upon g plus 1 because we have considered the unity feedback system. So after simplifying this m of s, I would obtain this expression. You can also compute by yourself to verify whether you have obtained this transfer function. Now we will qualitatively see the impact of the addition of this pole and additional pole at tp at minus 1 upon tp. So you see, as the value of tp increases, if the value of the tp increases, then it implies that the pole would be or would move closer to the origin, and if it moves closer to the origin, then it also means that it will move closer to the dominant poles. So in this case we will see the increase in the maximum overshoot, and the reason behind this point, pay attention to this transfer function whatever we have obtained at the closed loop transfer function. So we have this sum tp s cube. So first of all we will make the numerator polynomial as the monic polynomial, meaning to say that the coefficient of the higher uh, degree coefficient should be 1. Okay, so after dividing it by 1 by tp, so here let's say we will divide this whole expression by 1 by tp. So you would notice in this term I would have 2 xi omega n by tp. Yes, so this particular term. So since tp is of higher value, this tp is of higher value, and because of tp having higher value, this overall value would decrease, meaning to say that the damping of the system would decrease. Okay, now if and we had seen that with the as the damping decreases, then the maximum overshoot increases. Okay, this is the I think one of the responses we had seen earlier. Yes, here. So in this particular case, in the pre-discussion, if we have xi, if we have a decreasing xi, then the overshoot will become that the overshoot would increase, and for xi is equal to 0, we would have the maximum, the highest overshoot. So since the damping has been decreased, so we will see the increase in the maximum overshoot. Okay. Now the addition of the pole would increase the rise time of the step response. So this is the nominal behavior. Why? Say so if you see this transfer function once again, I can write this transfer function. Let's say some a times some second order polynomial and some first order polynomial, because this is a third degree polynomial. Okay, and this could be written, or you can visualize this as the two cascaded system. One is the second order system and another is the first order system. Okay, and in the first order system we have always seen that it would there won't be any overshoot, but the response will be delayed. The response would be somehow delayed to reach to its steady state value, and the same effect it will have the on this system as well, which amounts to saying that the rise time of the step response would increase, because if this first order system is not there, then we would have the nominal second order system, and with the first order system it is like adding a delay, some kind of delay to the system, and if we are delayed then the rise time would definitely increase. Now another important point here is that adding a pole to the forward path transfer function would reduce the bandwidth of the closed loop system, and we will come on to this later once we will come to the part of designing the controllers. Okay, so this you can take this as an homework problem where you have omega n is equal to 1, xi is equal to 0.525, and you have tp four different values 0, 0.2, 0.667 and 1. Okay, so these two parameters are of the first order system, and here we are adding an addition, we are adding a pole to make the system a third order system at four different locations. Okay, so plot the response for four different cases. You can do this in MATLAB, and you would notice that when TP become equal to 0.667, the system would become unstable. So this is an interesting point. That the interesting point here is that if I see this transfer function, this is the forward path transfer function. So without this term, this is a nominal second order system what we had seen earlier. Okay, so the location of the forward path transfer function we have at s is equal to 0, as s is equal to minus 2 xi omega n. Now if I add an additional pole which is also onto the left hand side, okay, now if I make the closed loop transfer function, then for Tp greater than 0.667 you would notice that the system becomes unstable, though all the poles except one where it is located on the origin, the other two poles are stable. But once you do the analysis in the closed loop system, the closed loop transfer function becomes unstable. Okay, so verify this by yourself. You can use the MATLAB to plot the responses. Hmm. Now the second point here is that if I add a pole to the closed loop transfer function, so say we have the closed loop transfer function y over r given by this. So this part is what we have been seeing so far from the beginning of this topic. Now in the forward part closed loop transfer function, I have added this pole located at minus 1 upon dp. Okay, now if we see that if the pole moves towards the origin, the rise time would increase. Huh? with the same justification what we had seen earlier, that the multiplication of any system with the first order system would increase the rise time. Now it also means that if I multiply another transfer function in which the pole located at TP2, let's say. Now the response of this fourth order system, you in this the response you would see the rise time further increases. So as you add the number of first order system, the rise time would increase. Okay, but the interesting point here is that the maximum overshoot will decrease now, which is opposite to adding a pole into the forward path transfer function, right? And the reason behind this is, now let's see once again this denominator polynomial. Okay, so in the denominator polynomial, in first of all let's see here. So in here we had this term in the damping, 2 xi omega n upon tp. And this appears because we want the monic polynomial and we divide the whole expression by tp in the damping term of s. Okay, so now in this expression, if I write only the damping term, or if I am only concerned with the damping term, so it would be 2 xi omega n, this is the s term, multiplied by this one, and we would have omega n square tp. Okay, so this is the damping term, or the coefficient of the s. Okay, so here you notice that as the value of tp increases, the value of xi actually increases, and with the increase of the damping ratio or the damping of the system, we had seen earlier that the overshoot will decrease. The system would become overdamped. Okay, so the important point to note here is that if I add a pole into the forward part transfer function, then it would increase the maximum overshoot. But if I add a pole in the closed loop transfer function, then the maximum overshoot will decrease. In both the cases, with respect to the rise time, it would increase in both the cases. Either I add a pole into the forward part transfer function or the second order transfer function. Now this was all about adding a pole to the transfer function. Now if I add a 0 to the closed loop transfer function. So first of all, let's say we have this ms, m of s is equal to y upon r. This is the denominator polynomial of the second order system. We have just added this term. Okay, where a 0 is located at minus 1 upon tz. So on adding a 0 to the system or the closed loop transfer function, we shall see that the rise time would decrease. So there is a trade-off with the addition of the 0 and the addition of the pole. If I only add the pole into the closed loop transfer function, we see that the rise time increases. But if I only add the 0, we see that the rise time decreases and the maximum overshoot increases. So there is a trade-off in both the parameters, both the transient performance, rise time and the maximum overshoot. Okay, and the reason behind this, let's consider a general case where we have m of s is equal to y by r. Uh, if I just express this or decompose this as a summation of two transfer functions. So first of all is this one because of the 1, and the second appears because of this tzs. Now in the time domain, Excuse me. Now in the time domain, this is the y1 as a pure response of the second order system, and this I can express this as by using the property of the Laplace transform as tz times the derivative of y1, and this derivative appears because of this s term. Okay, so if you see the step response, that this is the original response of the second order system plus tz times the derivative. So whenever you have the derivative, your response would become faster, and if the response becomes faster, then the rise time would decrease. Now with the uh, response becoming faster, meaning to say it tried to achieve to the steady state value as fast as possible, due to which it could lead to increase in the maximum overshoot. So because of the inclusion of this derivative in the overall response of the system, you analyze these two behavior, the decrease in the rise time and increase in the maximum overshoot. Now if I add a 0 to the forward path transfer function, considering the case of a unity feedback system, so here I have considered g of s as 6 times 1 plus tzs. So this is the additional 0 into the forward path, and in the denominator polynomial I have ss plus 1 s plus 2. So if I write the closed loop transfer function, considering this forward path transfer function, I would obtain this one. Okay, so now see here. Now we have 1 plus tzs appearing in the numerator of m of s. Okay, and in the previous analysis we had seen if there is a 1 plus tz of s in the numerator, you would see the decrease in the rise time and increase in the maximum overshoot. So the similar behavior you would expect to see here, but at the same time the damping has changed here, which is different to this one, because here the damping was not changed. It was because of the derivative kick you was seeing an increment in the maximum overshoot. But we know from the formula that the maximum overshoot is highly impacted by the damping of the system. So one, so here uh, you also see that tz appears in the denominator, meaning to say that it would improve the damping or it would lead to the maximum overshoot. Okay, so there is both the analysis, both the behavior you would see increment in the maximum overshoot because of this factor and the reduction of the maximum overshoot because of the improved damping. Now which factor will impact the most or would have a dominant effect on the overall response? Uh, it is a question we will address while designing the controller, because here we have done the separate analysis. First we had seen only addition of pole, and the separate analysis we had done only addition of 0. Okay, now in the controller, let's say I design some controller C which contain both poles and zeros, and we had seen for only addition of poles and only addition of zero the effects are quite opposite in the transient specification. So now it would depend on the location of the zero and the location of the pole, that which will dominate in the overall response of the closed loop system. Okay, so this we shall analyze while designing the controller. But the important point to note here is if I add only the poles, how the transient performance is impacted. If I only add the zero in either in the forward path or in the closed loop transfer function, how the performance is affected. Okay, so uh, this ends up our this topic on time domain analysis. The only part which is remaining in this topic is about the solution of the state space system. Okay, and because we had seen for the transfer functions that how you can write the solution, but we have also seen another representation of the same system by using the state space representation, and we know that the state space representation is basically a first order derivative, but in that first order derivative you have to deal with the matrices. So how to obtain the solution and how you can write it into a compact form, this we will take up on in the next class. Okay, so now if you have any doubts or queries, I can take them now or in the tutorial problems. Mm-hmm. Yes, Nagpal. Mm-hmm. Why it makes the response faster, is it the question? Okay, so see, this you can analyze by doing some both the type of analysis, qualitative and quantitative. First of all, I will suggest you to let's say consider this example. Okay, where I have specified omega n xi as these value 1 and 0.25. Now to see this situation, add a 0 into the uh, closed loop transfer function. Okay, and plot the responses. I don't have the response here, or maybe I have a response. Let's see. Okay, so here it is. So in this particular example, mm, so I have some system, nominal system. So this one, we the response which I get. Let's zoom this figure so you're able to see it properly. Okay, so this response is no zero. Okay, now if I add a zero more closer to the origin, which is this one, so we see that the maximum overshoot increases. And now even if I move the 0 further from the origin, which is at -5 and -10, the maximum overshoot would still increase with respect to the response obtained without no 0, without the 0. Okay, so the basic idea is, let's say we have y1 of t, this is the response. Now if I add in this response the derivative of this one, meaning to say basically I am, let's say at some point, adding a tangent. If you compute a tangent, hmm, so adding a response to the original response, due to which the maximum overshoot will increase. So in this particular example you would notice that in comparison to the response obtained with no 0, you see a rise in the maximum overshoot with any 0 located. Now only it depends on the location of the 0 that how much contribution it would make to the increment in the maximum overshoot. Okay. Mm-hmm. If you Yes, the frequency remains same. It's only, say for example, let's consider this one C1. Okay, this is the response of a pure second order system. Now if you take the derivative of this one, and add it into the response of C1, we are not saying that the frequency would change, but it would uh, add some terms, and possibly the phase of the system would also change. And this is what we are seeing here, right? So if you see, in fact, in the four different responses, the frequency has not changed. The tick, you see this frequency, and in the further terms, sorry, this one, the frequency component remains the same. Okay. Yes. mm, Possibly yes. Say for example, let's say we have this s plus a, okay, c of s, where c is the output transform, and I have added some 0 located at minus a. So this I can express as s of c of s plus a of c of s. So the overall response of the system with a 0 now consists of two parts: the derivative of the original response plus a scaled version of the original response. Now if a, the negative of the 0, is very large, then the Laplace transform of the response is approximately a c of s, a times c of s. And this is what we have seen here, that if the 0 is located very far from the dominant pole, then it would almost become equal to the response having no 0. Now if you, let's say if a becomes negative, if a becomes negative, then there is much more problem. Okay, because the system now it becomes a non-minimum phase system, meaning to say now we have a 0 located onto the right hand side, which implies that the response will initially follow the derivative in the opposite direction from the scale response. You see, so for the non-minimum phase system, generally we have this response kind of thing. Okay, first it because of this term, the non-minimum phase, it will go into the opposite direction and then it will increase. You see, so the behavior would become completely different, which is much more problematic to analyze. Okay. Yes, I think it depends on the value of the damping ratio. Yes. Mm-hmm. Mm-hmm. Mm, what do you mean? What do you? Yes, Ts is 4 upon xi omega n when xi is between 0 and 0.9. So we come up with this approximation. So let me see where we have these formulas. Okay, here the settling time. So TS, we said that this is one you're talking about, right? Nilotpal? Okay, so here we have TS is equal to 4 upon xi omega n. So we said that this is a very conservative estimate. Okay, why this is a very conservative estimate we had seen when we did the computation. Now, generally the settling time you generally obtain it by plotting the responses. But in many textbooks, generally you find this formula. But it might be possible that for some system where uh, where you have xi less than 0.69, you see this behavior where Ts is inversely proportional to xi and omega n, which is basically this one. Okay, but for xi greater than 0.69, you would see that Ts actually becomes directly proportional to xi. So 0, yes, so we basically this comes from the frequency domain analysis when we come on to the the computation of the bandwidth of the closed loop system. Okay, so this particular value 0.69 we will see there. So that is why I say that these formulas are or this formula particularly is quite conservative estimate of the settling time. But generally if you want to analyze do the analysis of your closed loop system for the settling time, it is always better to do it by plotting the responses and adjusting the response or adjusting the response by designing the controller so that you can get your desired settling time. Okay, it is in a similar way that the settling time we have defined a some window. If you recall that for settling time, basically we have defined some window, this window, where we have 0 point plus minus 2% around the steady state value. But this is not a fixed rule, right? This is not a fixed rule. It could be plus minus 5%. So in that case, the formula would change because this formula we have obtained particularly for plus minus 2%. But what we are really interested in that how the settling time is affected with the particularly two parameters, the damping ratio and the natural frequency omega n. Okay, so if you have any other queries or issue regarding the total problems, so I think the submission of the total problems would be open until tomorrow late afternoon. So I would suggest you to submit your solutions. So if we do not have any other queries, then maybe we can disconnect it now.